Okay, so I promised you some examples, and here we go. Let's look at this one right here, silver chloride. It is incredibly insoluble. KSP is equal to 1.77 times 10 to the negative 10th. Okay, it really does not want to dissolve. Okay, that equilibrium lies very far to the left. Why does it dissolve at all? Okay. Well, there are two ways of looking at this problem. First off, delta G equals delta G standard plus RT log Q. For the equilibrium, okay, silver chloride dissociates into silver 1 plus and chlorine 1 minus. Okay. Let's say there's no products at all. All we have is reactants, just the solid silver chloride sitting at the bottom of a glass of water. Okay. If there's no products, that means Q is equal to 0. And if Q is equal to 0, well, what's the natural log of 0? It's undefined, actually. It's negative infinity. Okay? So just looking at this problem right here, if you don't have any products, you're always going to make some product. Okay? You have to. There's just no way not to. It might take a billion years, but it'll happen. In the case of silver chloride, it actually happens almost immediately. It just doesn't go very far because it builds up that product almost immediately. All right, the other way to look at it is to look at the reaction itself. Okay, so silver chloride, solid, in equilibrium with silver 1 plus, aqueous, and chlorine 1 minus, also aqueous. Those aqueuses are important. Okay? Look at delta G equals delta H minus T delta S. Which side of this equation is higher in entropy? The solids sitting at the bottom of the glass, or the ions floating around? It's the ions floating around in solution. The ions. It's always the ions. Well, not always the ions, but it's the ions floating around in solution. Okay? They're free to move. Okay? So that is going to be higher in entropy than the reactant side of the equation. Now, higher in entropy means that increase in entropy, tends to be spontaneous. And yet we know from the fact that KSP is really small that delta G is positive. This is not a reaction that wants to happen. It's a Dursley reaction. So that means that delta H must be negative as well. Okay? It must be a very endothermic reaction. So that's why silver chloride doesn't dissolve. I mean, there are other possibilities. This is just, guesstimation based on some very simple observations. But those are very good sorts of guesses. I'm making them, so of course I think they're good. But there are other possibilities that I can think of, but I will avoid going into those. Let's move on to our next example. Hydrogen plus oxygen yields water. Okay? That's lower in entropy, so why does it happen? Well, why do I say it's lower in entropy? Because you have 2 hydrogen molecules plus 1 oxygen molecule, that's the balanced reaction, yields 2 molecules of water. Okay? That's 3 molecules of gas going to form 2 molecules of gas. The water produces, it's gaseous water when it's formed, mostly. So why does it happen at all? Okay. Well, just think about what happens when you combine hydrogen and oxygen to make water. It's a big explosion. It's because the reaction is incredibly exothermic. Okay. You would have to get very, very, very low temperatures to prevent hydrogen and oxygen from combining to form water. Incredibly exothermic. Now, why does increasing temperature increase solubility for solids? Well, think back to the silver chloride example. You have the solid on the reactant side, and you have ions in solution, aqueous, on the product side. As you increase temperature, you're increasing the importance of entropy. Okay? Entropy dominates at high temperatures because of T delta S. Enthalpy dominates at low temperatures. Okay? Because the lower the temperature, the smaller that T delta S factor becomes. So that means that higher entropy processes will be more likely to happen at higher temperatures. So dissolving in solution is something that increases entropy because you're going from a solid to an aqueous thing. So increasing temperature is going to increase solubility for solids. But let's take a look at the gases. You have exactly the opposite situation because a gas is more free when it's not in solution. It's less free when it is in solution because it's no longer a gas. Gases are ridiculously high in entropy. They are very low in entropy when they're dissolved because they're not able to move as much. They're not able to move as fast. They're not able to explore space. And suddenly they're surrounded by all these water molecules that want to interact with them. Okay? So that interaction, those non-bonding interactions that you see between water and stuff dissolved in water, okay, that's a sort of a bond. That's an association. Okay, that's bringing you more toward the solid side, okay, from the gas side. So at higher temperatures, you favor the higher entropy sort of state, and a gas is going to be higher entropy than any sort of dissolved liquid or aqueous solution. Okay? So that's why you see the opposite sort of interaction between dissolved solids and dissolved gases with respect to temperature. All right, those are all the examples I have on tap, and I will see you in class, because that is the end of Chapter 16.